Hi all. Last time we left off talking about the concept of absolute convergence versus conditional convergence. And right now I'm going to give you a proof of the last theorem that I talked about, which is that if a series of absolute values is convergent, then the series itself, before taking absolute values, is also convergent. Okay, and the proof it relies on the comparison test, as you might expect. So one thing that we know about the absolute value is that the negative of the absolute value and the positive of the absolute value bound the true value. And that's because you're either equal to the upper bound or you're equal to the lower bound. It's one of those two places. Either way, this is satisfied. So given that this is true, I can add absolute value to all parts of this inequality. And what I'll get is an plus absolute value of an is less than 2 times an. And both are positive, are non-negative. Okay? When you have series with non-negative terms, you can apply the comparison test. Okay. The series of terms 2 times absolute value of an, well, we're allowed to factor that out by the laws of series. Okay, whenever you have a constant multiplied by each term, assuming of course it's a convergent series, you can pull the constant out. So this is convergent. And so that implies that the series the positive series whose terms are less than that is also convergent. And that's by the comparison test. Okay. Well, if this is true, one of the other rules of series is that if I have two convergent series, then I can subtract the terms and I'd still get a convergent series. So I know this is a convergent series, and I know that the series with absolute value of an as its term is also a convergent series, so this must converge. But this is just the series an. Okay, so that proves this theorem. So that's why whenever we have a series which converges absolutely, we can assume that it converges no matter what signs you attach to it. Okay. Now we're going to go through a couple of tests that apply, which we can use to determine absolute convergence. We'll start with the ratio test. Okay. Let's let L equal the limit as n goes to infinity of a sub n plus 1 divided by a sub n. Okay. If L is less than 1, then the series a sub n is absolutely convergent. If L is greater than 1, then the series is divergent. If L equals 1, then the series is, then the test is inconclusive. Quick question. Make sure that we've got the right concepts in mind. If a series A sub n is conditionally convergent, what do we expect the result of the ratio test to be? Okay, so think about that for a moment. Given the different outcomes of the ratio test, what must the outcome be for a conditionally convergent series? Well, we must get L equals 1, because otherwise it's either divergent or absolutely convergent. Okay, that's not to say that if it's inconclusive, it's conditionally convergent. You could have absolutely any outcome for L equals 1. You could have divergence, you could have absolute convergence, and you could have conditional convergence. Okay. So let's give this ratio test a try. Suppose we have the series given by sum from n equals 1 to infinity of minus 1 to the n squared over 2 to the n. Okay, we're going to try and apply the ratio test. Okay, so the ratio test says, apply the ratio test. Ratio test says if I take the limit as n goes to infinity of the absolute value of this term for n plus 1 divided by the same term for n, I'm going to ignore the sign because it'll end up getting thrown out because of the absolute value. So I'll just take n plus 1 squared divided by 2 to the n plus 1 divided by n squared over 2 to the n. Okay, so reciprocating and multiplying, I get limit as n goes to infinity of 2 to the n times n plus 1 squared divided by 2 to the n plus 1 times n squared. This is equal to limit as n goes to infinity. And because I have no negative terms in here, I'm going to drop the absolute value signs. This is 1/2 times n plus 1 over n squared. And this, I can put the limit inside of the square because the square is a continuous function. So I'll get the limit, the 1/2 times the limit as n goes to infinity of n plus 1 over n squared. This limit is just 1 because it's the quotient of the leading terms. So I get 1/2. Okay? That's our L. Now given that L equals 1/2, I look back at the various outcomes of the ratio test, I see when L is less than 1, I can infer that this series is absolutely convergent. Okay. Let's try one more. We're going to take the sum from n equals 1 to infinity of n to the n divided by n factorial. Okay. So I think we looked at this actually in one of the problem sessions. But let's apply the ratio test. So again, we take the limit as n goes to infinity of a sub n plus 1 divided by a sub n. This will be equal to the limit as n approaches infinity of n plus 1 to the n plus 1 divided by n plus 1 factorial divided by n to the n over n factorial. Okay? And I'm going to drop the absolute value signs because everything in here is positive. Reciprocating and multiplying, we get n factorial times n plus 1 to the n plus 1 divided by n plus 1 factorial times n to the n. Okay? Well, n factorial is the product of the first n integers, and n plus 1 factorial is the product of the first n plus 1 integers. So I can actually pull out that last integer, and what this equals is n factorial divided by n factorial times n plus 1. Okay? Because it's just, this is the first n integers, and this is that n plus 1th integer. And then over here, I'll get carry over the same thing. Okay. So I get cancellation of the n factorials. And I can also cancel one factor of the n plus 1. I'll do that here. Cancel this and cancel that. Cancel this, cancel that. And we're left with limit as n goes to infinity of n plus 1 divided by n. And both of these are raised to the nth power, so I can just include them in the same fraction. This might be a little more familiar in this form, as limit as n goes to infinity of 1 plus 1 over n to the n, which is a classic formula for E. Okay. So looking back at the expressions, at the outcomes of the ratio test, we need to know if E is less than or greater than 1. And E is about 2.718. So that's clearly greater than 1. So our series diverges. Let's say you forgot this limit. How could you go about figuring it out? So Let's make a brief tangent to do that. One way you can do that is you could say, let's assume L equals limit as n goes to infinity of 1 plus 1 over n to the n. Okay? It's fair to assume this isn't anywhere near 0 because it's always a positive power of something that's larger than 1. So we can take the log of both sides without running into the discontinuity of log. And then I can pass the log inside of the limit. Okay? When you have log of a power, you can bring that power down. And then, given this indeterminate form, because log of 1 plus 1 over n is going towards 0 and n is going towards infinity, we can express it in a form that's susceptible to L'Hopital's rule. Okay? Because multiplying by n is the same thing as dividing by 1 over n. Okay? By L'Hopital's rule, this will be equal to the limit as n goes to infinity of 1 over 1 plus 1 over n times the derivative of this. Again, we're considering this as a continuous function, so there's a bit of abusive notation here. Minus 1 over n squared divided by minus 1 over n squared, which is the log of 1 over n. The derivative of 1 over n. These two cancel, and we're left with the limit as n goes to infinity of 1 over 1 plus 1 over n. And if we simplify that fraction, it's going to be n over n plus 1. And this is clearly 1. So if log of L equals 1, that means L equals e to the 1, or e. That's one other way to derive the value of that limit. But fair to say, when you see an expression that looks like this, start thinking about e. Okay, so those are two applications of the ratio test. Similar test called the root test. Okay, let L equal the limit as n approaches infinity of the nth root of the absolute value of a sub n. Okay? Then there are three cases as before. If L is less than 1, then the series is absolutely convergent. If L is greater than 1, then the series is divergent. And if L is exactly equal to 1, then the test is inconclusive. Okay. The root test and ratio test have a lot in common, and in fact, their success is interconnected. And what I mean by that is, if the ratio test is inconclusive, then the root test will also be. And that's true vice versa. If the root test is inconclusive, then the ratio test will also be inconclusive. So you might ask, why would I want to have both tests if they're equally as effective? If when one is inconclusive, the other is inconclusive? Well, the answer is that there are examples where one is easier to perform than the other. It's easier to compute a certain limit than it is to compute a different one, even if the limit is 1 in both cases. Okay. Let's look at an example. Let's take the sum of 9 to the n divided by n plus 1 times 2 to the 3n plus 1, where n goes from 1 to infinity. So we'll apply the root test. Okay. L will be equal to the limit as n approaches infinity of the nth root, and I'm going to write this as an exponent of 1 over n. And inside here, I don't actually have to perform the absolute value because everything is positive. Okay, and I'm raising this to the 1 over n power. Okay, because everything in here is multiplied or divided, with the exception of this n plus 1, which I'll treat as a single unit, I can distribute the power. So what I get is 9 to the n to the 1 over n is just 9. 2 to the 3n plus 1 divided by to the 1 over n power is 2 to the 3 plus 1 over n. So I'm just going to put the 2 to the 3 out here. And then what remains inside is n plus 1 and 2 to the 1 over n. Okay, so I left one of this factor of 2 in here so that I could kind of ignore it. And what do we have here? I can factor this 9 over 8 out of the limit. I'm left with 9 over 8 times limit as n goes to infinity of 1 over 2 times n plus 1 to the 1 over n this limit will end up being equal to 1. And that needs a little more justification, which I'll leave for you to do. But when you complete the test, you find that L is equal to 9/8, which is greater than 1, and that tells us that the series diverges. Okay. Let's take another example. Let's take the series as n goes from 1 to infinity of 3n divided by 5n plus 1 raised to the nth power. Okay, well, let's apply the root test. And one way to tell that the root test will be particularly effective is that you have a power of n here. So when you take the nth root, that's going to cancel very nicely. So the limit as n goes to infinity of the nth root of 3n over 5n plus 1 raised to the nth power, and that's raised to the 1 over nth power. So obviously n times 1 over n is 1, so we're left with the limit as n goes to infinity of 3n over 5n plus 1, and this is equal to 3 over 5. This is less than 1, which means that the series is absolutely convergent. Okay. And that's a good tip to keep in mind. Powers of n are suited to the root test. Okay. Let's do another example. If we have the sum from n equals 1 to infinity of 2n factorial divided by n factorial squared. We're going to try to determine the convergence of this series. So I'm going to say we should apply not the root test, but the ratio test. Okay. We're going to take limit as n goes to infinity of a sub n plus 1 divided by a sub n. This is equal to limit as n goes to infinity of 2n factorial. My video got cut off while I was doing the last example. We were looking at the series, the sum from n equals 1 to infinity of 2n factorial over n factorial squared. And seeing the factorials, I decided to use the ratio test rather than the root test. We took the limit as n goes to infinity of the absolute value of an plus 1 over an, which, subbing in the formula for each term, we have limit as n goes to infinity, absolute value of 2 times n plus 1 factorial divided by n plus 1 factorial squared divided by the general term 2n factorial divided by n factorial squared. Okay, we dropped the absolute value marks because all of the terms inside were positive, and then we regrouped a bit. The 2n factorial goes into the denominator, and the 2n plus 2 is the same as 2 times n plus 1. And then with the other terms, we get n factorial squared on top, and we have n plus 1 factorial squared in the bottom. So doing a lot of cancellation with factorials, we know that 2n plus 2 factorial is the first 2n integers, so it's 2n factorial times 2n plus 1 times 2n plus 2. So that's why we get this numerator. And n plus 1 factorial, when we cancel n factorial, we're left with n plus 1. Since we have two factors of that, we get 2 factors of n plus 1. And then taking the limit as n goes to infinity, we can just take the ratio of the leading coefficients here. The leading coefficient on top is 4n squared. The leading coefficient on bottom is n squared, so we're left with 4. As we know, 4 is greater than 1. So the series diverges by the ratio test. And this is just an example of how factorials work really nicely with the ratio test, because there's a lot of cancellation that can happen. Okay, that's it for me. Thanks.